Recording is rolling. It's Thursday, September 23rd. Yesterday, you guys did this double elevator Atwood lab, and today you guys are going to do the modified version, which is going to involve a horizontal component. So remind you guys that there's homework that's due tomorrow. I've gone over every problem type here. There's also a bonus homework, and you guys have AP Classroom. You're coming back from this upcoming weekend. So remind you guys some of how this lab was working. There were two main setups for the Atwood machine. There's the classic double elevator. This is the one you guys did yesterday. We drew these free body diagrams yesterday. So in the first minutes, I want to go over actually what the answers are to this lab. Remember, the question was, can you create an expression for the acceleration as a function of the input masses, right? and also the gravity field? Right? So of course, they're accelerating in different directions, but there's some magnitude of acceleration that's associated with that motion. Everything's tied together by strings. Right? And there are sort of two approaches. One is you could solve everything on paper with Newton's second law of motion. And I took you guys this far yesterday at the beginning class to create the free body diagrams. And yesterday, you guys got all the data, like the empirical data for this, so you could actually start to put that together. But I do want to go over the answers with you guys. So you guys can check your answers from yesterday. And also, you guys can know ahead of time what the answer is going to be to this modified version. So as you guys are grabbing your empirical data, you can see how close this is. Okay, so let's go do that. So I'll start with this double elevator. Call this double elevator Atwood. I don't know if anybody outside of the stream calls it a double elevator, but I do. So, I mean, I don't know if I want to write that term on an AP exam. I don't know if that confuse the grader, but just say Atwood. Okay, we got this. You guys know that the acceleration of the system, that's to say, this mass A moving down and this mass B moving up, is equal to net force on total mass. That's Newton's second law of motion. And then you just shop for the component parts and plug them in and solve for the acceleration. So the acceleration of the system. Well, the net force. So I did draw a few forces here. We got the weight of block A, the weight of block B. There's tension in the string. That's the same for both. You guys remember all the stuff going on yesterday? What is the net force? What would you guys say? Would it just be the difference between the two weights? Kind of like a tug of war that's just like maybe wound around a tree or something, right? This guy's pulling one way, this guy's pulling another way. And the difference between those two, I'll say the difference in the weights, M sub AG minus M sub BG, the difference in the weights represents the net force. And remember how that could be consistent too with some of the, we did some thought experiments that involve some boundary conditions. Like for example, if these were the same weight, same mass, same weight, what would the system do? Just kind of sit there, right? Like in equilibrium. And this is consistent with that because you'd be something minus itself, where it's the same number. This would zero out. So there would be zero acceleration in the system. And what's the total inertia that's being moved around? Isn't it just the two masses added together? MA plus MB? That actually could be the answer right there, but maybe just make this a little prettier. What I can also do is factor out the free fall gravity, like the gravity field. So the acceleration of the system, therefore, is equal to the difference of the masses divided by the sum of those masses, all multiplied by the free fall gravity of the planet. That is the answer to your guys' lab from yesterday. See, show of hands. How many guys figured that out? How many guys figured that out? Oh, yeah, about half the class. That is awesome. You guys figured that out. Any questions on that so far? Oh, and also, notice I did not put tension anywhere in this formula because tension is just an internal force. It's not driving the system to move. It's just holding everything together. Okay. Let's look at the double elevator that you guys are about to do. And then, again, if you guys got your empirical data, you can go back and look at the notes I'm about to give you and say, I wonder how close this is. Right, so, same idea. The acceleration, so I'll call this a single elevator Atwood. That's just my Griffin term for this. The acceleration of the system, one block down, the other block horizontal in this case, is, well, it's still net force over total mass. Isaac Newton figured that out hundreds of years ago. And what is the net force on this, driving the system to move? Only the weight of block A Yeah, mass A times free fall gravity. Okay. That's it. No, what about all the, I drew a bunch of other forces. Well, tension is still internal, just like it was for the double elevator. That's just holding everything together, so don't do that. And then the weight of block B is actually exactly canceled out by the normal force holding it up. Is that true? Oh, remember today, you guys get some new equipment. You guys get a Hot Wheels car. Doesn't that also add to the mass? Remember, the Hot Wheels car is about 30, 35 grams. I've got some scales back there. If you guys can get access to those, but if you can't, then how about maybe 35 grams if you include the tape, then probably went pretty close. But now what's the total inertia that's being moved around? Isn't it still the sum of the masses of the blocks? Where, well, I just told you guys that MB also includes the Hot Wheels car, so you have to also include that mass, right? It's about 30, 35 grams. Okay. Oh, that's the answer. That's it. Okay. So that's the answer to today's lab. You guys can confirm that experimentally. Questions so far? I want to do one more thing before I send you guys back there. I want to extend this to make this a bit more complicated. You guys got this in your notes? Everything you need? Okay. All right. So I want to throw you guys something that AP totally could ask, which might be a question like this. Suppose that they're, here, label these. Let's call this mass A. I'll call this mass B. Yeah, mass B. Okay. And let's say that there's also a coefficient of friction between these two surfaces. I'll call it mu sub K. Okay. And let's also suppose that, I'll say assume that mass A accelerates downward. Because if you get anything like this, then it might be ambiguous, especially if like mass B was a little bit more than mass A. Then you'd have to start to figure out, well, what is this angle? How much more? And then you have to do the full free body diagram, which I'm about to do with you guys, and then sort of, it could be ambiguous as to which way this is accelerating. So just to help you guys out a little bit, I'll let you know maybe it's going to accelerate this way. Okay. And the direction of motion, it would be especially important for which force vector that we're eventually going to put on here. Direction of motion really matters for always which force vector. Friction, because friction, sliding friction is always going to oppose the motion. Let's do free body diagram. And it's the same question as your lab question, it's just a more complicated setup. What is the acceleration of this system going to be? So I need to introduce a Cartesian system that runs parallel perpendicular to the surface, just like you guys have been doing for a long time in this class. Now that's specifically again applied to mass B. Let's throw in some force vectors. Now I know this mass A has a weight. I hope this is a pretty big force because sort of telling you guys ahead of time that it's going to be the dominant force here. M sub A times G, so that's the weight of this block. Mass B also has a weight. Maybe, I can even make a pretty similar weight and still there. So I'll call this M sub B times G, like that. Okay. So those are the two, you call these field forces, so Earth's gravity field, like pulling these down, this weight AP next to it. Okay. Driving system is. Well, let's take the weight of mass B and break that into components. So part of its weight is pushing into the surface, and part of it's trying to pull the whole thing counterclockwise. Interesting. That angle is that angle, whatever that is. Notice I'm doing everything in terms of variables. This could totally be an AP question. You guys see that this component here would be, well, you guys have done enough of these. You guys are staying a step ahead of me, right? This is the weight of block B times what? Yep, sine of the angle. And then, okay, so this one must be MBG times cosine of that angle. Okay. There is a normal force, which is equivalent to MBG sine, cosine theta. Cosine theta. Remember? Okay. As long as the string's pulling horizontally, then that would be true, that these two balance out. Okay. And finally, there's one more force I have to put on here. Which force is that? Friction, because I told you there's a coefficient of friction here. And here's where this assumption comes in. Okay. And if you didn't know if it was ambiguous, maybe, well, what you would actually do is you would compare in this vector right here, this component, MBG sine theta to MAG, and then whichever one is bigger is going to determine the direction of motion. Okay? And then friction will change the rate of acceleration of it, but I'll call this force friction like that. Okay? Now, and then actually I could add on a couple more forces. That's going to be mass A has a tension pulling up, which I'll make pretty big, but it has to be less than the weight of block A. So see how the weight of block A is a little bit more than the tension? Or try to draw it that way. Maybe I should exaggerate that a bit more. Also, big force pulling down. Okay, just pull it up. So the tension is less than the weight of block A. Okay. But that tension has to be also exactly equal to the tension pulling block B up the ramp. And I had to make it big enough to make sense from that point of view. Call this tension T. See how this tension T and this tension T, same magnitude? Okay. But this tension T, if you get everything proportionally exactly right, has to overcome two forces on block B. It has to obviously be more than the friction force, but also see this sine component of the weight actually has to be bigger than both of these put together, right? Because both of these forces are trying to pull block B down the incline, tension's trying to pull it up the incline, and it has to beat those two. Okay, so, and so, ooh boy, we got a real fancy free body diagram going on here. What's the acceleration of the system? Well, I need to identify the forces that are going to drive the motion. And I see three forces. Three forces I'm going to put into Newton's second law. What's one of the forces? That's going to be a Newton's second law of motion. How about the weight of block A? That's driving it clockwise. And the sine component of the weight of B is saying, no, let's go counterclockwise, as is the friction. So we got this force saying clockwise versus these two saying counterclockwise. You guys see it? Okay. Break out some paper and finish the second law of motion. Determine the acceleration of the system. So acceleration of that system is going to be, well, net force on total mass. Here's Newton's second law of motion. Okay. And that is, well, the net force. Now I'm juggling three driving forces that matter. So the weight of block A, so MAG, saying, let's go clockwise. And then these two opposing that, saying, no, let's go counterclockwise. So I'm going to subtract those off. So minus MBG sine theta minus the friction force. And that's all divided by, well, what's the total inertia being dragged around is still the sum of the blocks, just like it has been on your lab between yesterday and today. That true? Good so far? Okay. So here's the free body diagram. I circled the forces that I'm plugging into the second law of motion. Okay. Remind you guys real fast why I did not pick the other forces. Remember, tension is internal to the systems, just holding everything together. And the cosine component of the weight of block B and the normal force just balance each other out and that along that axis. Okay, so got these. All right. Now I'm going to do a couple more substitutions here. Just to clean this up, finish this off. Got a big old fraction going on. I know that the sum of the masses is in the denominator. That's the total inertia that's being moved around by the net force. What is the net force? These first two parts I'll just do the same. The weight of block A, saying let's go clockwise. The sine component of the weight of block B, saying no, let's go counterclockwise. But the friction force, can't we do a little substitution there? Maybe we'll do a substitution like this. Isn't friction force coefficient of friction times normal force? Coefficient of friction times normal force? And wasn't the normal force equal to the cosine component of the weight of block B? Guys remember that? These two are equal and opposite. So MBG cosine of the angle. A little substitution right there. That gets substituted into friction force, that expression right there. So to finish this off, this would be minus mu k times MBG cosine theta. Okay. Yeah. Now that might be maybe one of the tougher multiple choice questions that AP could ask, but that is definitely within the realm of something that he could get asked. They'd say, here's a incline type Atwood, what's the acceleration of the system, there's friction, boom, there's the answer. That's good? All right, so everything you need back in the lab tables, I will walk around and help you guys out.